Hello, everyone. My name is Meryl Keating, and I am a sophomore at the University of Washington studying mechanical engineering. And the research that I did was on insect robotics in space, specifically trajectory and landing. And my mentor for this research was Sawyer Fuller. And so you can see here on the left, this is the world's first fly-sized insect robot without a power or control wire. And what I was kind of looking into was seeing if insect robots like this could be used in space, and specifically being able to travel to Mars and back. And so what would be beneficial from this is the mobility, redundancy, coverage, and lower cost. And you can see in the bottom left is a picture of Ingenuity, which proved flight on Mars with the helicopter blades kind of resembling the wings of an insect robot. And so the first consideration that I had to think about when doing this research was how a carrier craft is still required to be able to protect insect-sized robots from space and radiation while they're traveling at very high speeds. And I mentioned this just now a little bit earlier, but the main reentry issues are speed and heat. So aero capture and aerobraking are used to be able to enter orbit and deorbit, releasing kinetic energy in the form of heat while slowing down from about 8,000 meters per second to 400 meters per second. And so in the lower atmosphere, you can see an example on the right, how a drag chute can be used. And so because of the insect robots being a smaller mass, this reduces the total energy to both escape orbit, transit, and deorbit, which is very beneficial. But what we still have to think about is what kind of carrier would be used to maximize efficiency. And so as I just mentioned, less mass means a simpler landing. You can see in the bottom left is a picture of Perseverance, which needed retro rockets to be able to hover and gently lower the robot onto the surface. But since insect masses are tiny, even with a carrier, they are a fraction of the weight, and they can use a much simpler balloon-like landing, like Pathfinder, or even fly away after touchdown. And here is a picture of the Python simulation of landing for past Mars landers. And I just use this as a kind of reference when I was working on the Python for the insect-sized robots in their carrier to be able to compare. So here are the first results. I had some assigned values, and these are based off the assumption that the carrier is around the size of a dodgeball. And so I had kind of assigned values of re-entry, velocity, radius, cross-sectional area, etc. And what I was able to compute from that is the ballistic coefficient, the max deceleration, and the max deceleration altitude. And you can see that all of that is represented in the graph below, which is time over velocity versus velocity in meters per second. So the overall scope of this research and kind of reason why we're looking into it is just to see if this is something that would be possible for the kind of following factors of mobility and flexibility, redundancy, coverage, and cost. And this is just a little ad lib that I wanted to kind of add in here, but I think it's really awesome, really cool that not too long ago, this kind of research was a secret. So I think it's really awesome that I was able to contribute to it a little bit and be able to learn more about its background. And these are the sources that I used. Thank you all so much for listening.